Good morning, ladies and gentlemen. Today I would like to present on my paper titled with Evaluation of Dynamic Measurement from RTK-GNSS Operating in Suburban Environment. I am Ravenny Sandin and Nahar as a presenter today, and I am from UITM Shah. For this presentation, I will include the introduction, problem statement, objective, methodology, result, and lastly conclusion. For the introduction, as shown in the figure 1, show that the RTK-GNSS positioning system was utilized to improve the accuracy in conventional GNSS. As shown in the reference 5, the author stated that the performance of RTK-GNSS receiver can be evaluated in terms of accuracy, integrity, continuity, and availability. Okay, next, we move to the reference 4. We can see that the author stated that 5 different types of low-cost RTK GNSS in terms of accuracy and availability was evaluated. For reference 6, the author stated that the performance of Leica Viva RTK GNSS receiver based on availability, accuracy, coordinate quality, indicator, and time to fix was evaluated. The performance on long-base RTK and network RTK using the accuracy of the positioning was evaluated in reference 7. Okay, we move to the problem statement. The first problem statement here is a performance of ambient-rich RS RTK GNSS on the accuracy and availability not sufficient to reveal noise characteristic in the residual. As in reference 8, the author stated that the error in the positioning are also contributed by color and correlated noise. Hence, color noise characteristic may need to be examined. The evaluation of integrity in GNSS measurement will be assessed by the probabilistic distribution of the error residual. For the fourth one, as stated in the reference 9, the author stated that the probability of the device providing a signal that is out of tolerance, the probabilistic distribution of the error need to be identified. The previous work in reference 4 did not evaluate the noise characteristic of the error of the ambient-rich RS. For our objective, the accuracy, availability, correlated noise characteristic, probabilistic distribution of the error need to evaluate measurement from the ambient-rich RS RTK GNSS when operating dynamically in suburban environment. Next, we move to the methodology. Figure 2 shows the ambient-rich RS which are able to receive signal from the different type of satellite. Figure 3 shows the rich view apps which are to identify the status of the signal from satellite. For figure 4, show the RTK GNSS setup. As we can see here, the base station need to be placed in the open area. Meanwhile, the rover need to attach in the top of the car, and the connection between two of it is a LoRa. For figure 5, show the serial communication between rover and MATLAB. As we can see here, the ambient-rich need to connect to the laptop via micro USB. For figure 6 and figure 7, we can see that two locations has been chosen for the experiment. As we can see, the X mark is represent the base station and the red line indicate rover navigate along the road. Figure 8 shows the flowchart of data logging algorithm. The algorithm extract GP-GGA message to acquire the latitude and longitude of the geodetic coordinate location of the rover and the quality of the log point. Each geodetic coordinate data will be logged into the MATLAB database. The quality indicator from the GP-GGA will also log to check the solution status as a single, float, or fixed point. For figure 9 shows the flowchart of the performance evaluation. First step is do the data logging using ambient-rich RS. After that, clean up data to remove outlier and flow data. The third step, construct georeference map using QGIS, also known as Quantum Geographic Information System software. From this one, 14 fixed point coordinates were collected using ambient-rich RS as a georeference point to construct an accurate real-time map for location A and location B, and lastly, do the data analysis for this project. From the data analysis, the positioning availability of the log data is analyzed using quality indicator to investigate the single point, floating point, and fixed point. Secondly, to calculate the mean absolute error and root mean squared error between ground truth reference and log data, MATLAB algorithm has been developed. To obtain the histogram, autocorrelation, and partial correlation, error residual from log and reference data need to be analyzed. To evaluate the probabilistic distribution of the error residual, MATLAB probabilistic distribution filter has been used. Next, we move to the result of MAE, RMSE, and position availability. Table 1 shows the position availability at location A. As we can see here, dataset 1 has the highest floating point that count with 98.33%. Dataset 4 has the highest fixed point that count with 38.48%. And dataset 7 has the highest single point that count with 2.94%. Dataset 3, 4, 5, 6, and 7 has the highest beta position availability compared to dataset 1 and dataset 2 due to the fixed point solutions. Table 2 explains on the MAE and RMSE of 2D position at location A. As we can see here, the lowest MAE and RMSE is dataset 4 that count with 0.2669 meter for MAE and 0.2861 meters for RMSE at the dataset 4, which means the highest is dataset 1 that count with 0.5408 meters and RMSE is 0.5828 meters. The performance of MAE and RMSE of dataset 1 and dataset 2 has the highest compared to the others dataset due to the fixed point solutions. Dataset 4 has the best MAE as it comes 38% of the fixed point coordinate, highest among the other dataset. Table 3 shows the position availability at location B. As we can see here, dataset 4 has the highest floating point that count with 92.33%. Dataset 6 has the highest fixed point that count with 9.19% and the highest single point that count with dataset 5 and dataset 7 that count with 34.70% and 33.23%. It will be affected to the MAE and RMSE result. Table 4 shows the MAE and RMSE of 2D position at location B. As we can see here, dataset 1 has the highest MAE and RMSE that count with 0.5787 meters for MAE and 0.8593 for RMSE, and the lowest one for the MAE and RMSE is dataset 4 that count with 0.3803 meters for MAE and 0.5069 meters for RMSE. Most of dataset has the highest MAE and RMSE due to cloud obstructions, distant rover from base, and random noise during data logging. Next, we move to autocorrelation and partial correlations. As we can see here in the figure 10, show the autocorrelation in the location A, and we can see the red line is represent random correlated noise. Meanwhile, the blue line is represent upper and lower bound. As we can see here, all 7 data sets from the location A is the red line is exceeding the blue line. The same goes for the partial correlation in location A, autocorrelation in location B, and lastly partial correlation in location B. This means we need to produce the probabilistic distribution inside this experiment. Figure 16 shows the fitting distribution for data set 5 of location B. As we can see here, only non-parametric distribution was being chosen for the fitting distribution. As we can see here, the probabilistic curve fit more than 80% of histogram data. Meanwhile, in figure 17 shows the non-fitting distribution for dataset 5 of location B. We can see exponential extreme value, generalized extreme value, logistic, log normal, normal, and Weibull has been chosen for non-fitting distribution because the probabilistic curve fit less than 80% of histogram data. And lastly, for the conclusion, MAE and RMSE indicate the accuracy of RTK-GNSS was highly affected by the multipath error and the presence of random noise in the suburban area. Inaccuracy could be attributed to the interference in LoRa radio frequency and unstable RTK settings within ambly-rich RS. To estimate the mean and the bound in the error, non-parametric probabilistic density has been used. Appropriate filtering method may need to be applied to process random correlated noise in order to improve GNS measurement. That's it for my presentation. Thank you for listening. I hope I can see you again in the future. Thank you.